I'd like to welcome everybody to the session on fairness and human values in AI. We're going to be hearing short talks from two faculty at Michigan AI. The first one is Lu Wang, and she's a member of Michigan AI, and she's an assistant professor of computer science and engineering at the University of Michigan. She investigates large-scale natural language understanding, including discourse analysis, argument mining, and text summarization, and more generally, computational social science. She earned her PhD from Cornell University and was on the faculty at Northeastern University before joining us last year. Her talk is titled, "Convince Me If You Can, Natural Language Generation for Argumentation." Lu?
Yeah. Hello, everyone. So please allow me to share my screen. Hopefully, everyone can see them correctly. So I am under a lot of pressure after, Melanie's talk and also all this conversation between AI and NLP, like whether AI can really understand natural language. So, but here we are. So I'm going to talk about how we can use natural language generation techniques to teach machines to perform argumentation. All right. There we go. So let's start with talking about what is an argument, right? So an argument contains reasons to persuade us whether an action or an idea is right or wrong. So they're closely related with opinions. But the key difference is that opinion can be one's own personal feelings, which means it doesn't have to be supportable. But for an argument, it is an assertion or a claim that is supported with concrete real-world evidence. Arguments usually don't exist by themselves, but rather they interact with other arguments. And this process, we call them argumentation. So why do we care about arguments? So argument understanding, assessment, and construction, they're crucial elements for decision-making processes. They could be ranged from complex decisions like which treatment that we should follow for a patient, or to simple questions like, which movie should I watch tonight with my friends, right? So they're also very prevalent. We can find them in online reviews, patent documents, like they help us to understand core decisions. We hear arguments in political campaigns to decide which candidate to vote for. And as researchers, we constantly make arguments in the papers and we interpret them from other people's work. So in particular, I'm interested in two research questions. One is, what makes argument persuasive? And the other one is, how can we teach machines to argue like a human? So in this talk, I'll focus on the second question, where we want to investigate whether machines can operate with facts, beliefs, values to perform logical reasoning, which is actually a critical step for building machine intelligence. All right, so one of the tasks we work on is counter-argument generation. For example, the definition for that is given a statement of belief on some controversial topic, and we're going to generate a counter-argument to refute that statement. There are different applications for this task. For example, it will help students learn to write essays and teach people to become better debaters. Of course, and in general, it will nurture critical thinking for the public. So here I'm going to use one example to demonstrate what actually needs to be learned in this task. Here, our input statement is death penalty is more rational than life in prison. So to counter-argue this claim, we cannot just basically stack all the evidence we have together. We actually will need diverse types of argumentative components to make a persuasive argument. And for example, in this case, we have functional language, like in theory, I agree with you. And then we also need to propose a central claim, like in reality, we will never have a perfect justice system, followed by different types of premises like reasoning and evidence to support it, right? So here there is unreliable evidence is used when there is no witnesses, which could result in wrongful convictions, so on and so forth. So as you can tell, This is definitely not an easy task because it requires different propositions of different types, and they're not just standalone propositions. There should be support relations among them. So it requires a lot of different types of relevant knowledge, and also we have to properly organize the information in a coherent and persuasive way. So how can we train models to do this? Traditionally, a natural language generation system needs to do three things. We start with content selection, basically what we're gonna say here, and followed by text planning, where we figure out when to say what. Basically, we need to give an order of the content. And finally, we do surface realization, basically how we can say that in a fluent language. But modern generation systems are not doing this. They're not create solutions for each of those components, but rather we would build end-to-end trained neural networks. And usually what we're gonna do here, I just show a standard like framework where we have an encoder, right? First reading input, for example, our input statement. And then we use a autoregressive decoder to output tokens one at a time. So these models, they work like a black box. Not only that they're not interpretable, but also the generations are also far from satisfactory. Here I can show a real output from a end-to-end trained neural network. Let's say we have a proposition saying gun control will do nothing to solve gun violence. And if you look at these end-to-end trained models output, firstly, the generation is pretty blunt. It doesn't have many different like concepts. It always says that gun control is bad, gun control is a good thing. The problem is that it's not a bad thing. So it's just keep repeating the same idea again and again. Despite its fluency, the discourse doesn't move forward with interesting concepts. And second, it's also incoherent, right? So if you look at sentence says, if you don't want to have a gun, you need to be able to get a gun. It doesn't make sense, right? So indeed, we actually find a lot of contradictory content or like nonsense, so generated by the neural networks. And the last thing is interpretability, right? So this has been brought up by many of today's speakers, right? It's like users don't really know why the text is generated in this way. And not only that, if you go the other direction, users also don't know what I can learn from those model behavior, right? So interpretability is not just about we understand the model's behavior, but it's also like, can I learn anything useful that I don't know before? So in our work, we have two objectives. One, we want to basically generate interesting and relevant content. So to do so, we want to add a retrieval component. Our second objective is that we want to make sure the output is coherent, and which also use different types of propositions like we have seen in the previous example. So here we propose a modular design of neural architecture, and we also add a language style control. So we make sure that the language also has some sort of like diversity here. I'm going to use one example to demonstrate how exactly our system works. And for technical details or system implementation, please feel free to check out our papers and project pages. So I'm not going to show those formula here, but they can be found in our paper. So our modular system consists of three modules. We're going to start with retrieval. So basically, we first use the given proposition to get relevant passages from large search engines, where only the passages of the right stance will be kept. And then from there, we're going to keep all those key phrases, which we can use for the downstream generation. And to build this like argument retrieval search engine, we want to leverage sources with both subjective and factual content. And in this case, we consider Wikipedia and also 4 mainstream news portals. Of course, you can add more of those. So in our study, we started with this 4. So they're sorted from the left to right based on their political leanings. In total, we have 12 million articles. In this case, we want to make sure that our data set actually covers different perspectives from different resources. So after we retrieve those passages and identify the key phrase we want to use, In the content selection and the planning component, we will generate sentence level representation by selecting key phrases in sequence, right? So for example, in the first sentence, our system decides not to select anything because we want to start with some, general functional language. And then we pick a core idea on restrict access to firearms. And the next, we will basically trying to use some evidence to support our stance. So here are some of those. And finally, we will collect those phrases that can help us to form logical reasoning. And after we do the content selection, in the final stage, we will do surface realization. So that is where we generate the fluent sentences. And here we want to add a style control where we want to have different types of arguments in the output. So in this case, for example, we consider argumentative function, right? So this is more for debate style, like language that used in those contexts, such as I disagree with you, or in theory, I agree with you, right? So like we would have seen. And based on the selection of the key phrases in the second sentence, right now we can, throw out our central claim saying, restricting access to guns will absolutely reduce gun violence. So the second sentence has a style of claim, which actually is predicted based on a machine learning model, specifically neural network model here. And for the first sentence, because we have said we want to use some evidence, so this one will have a type of premise, and it's going to use for forming, logical reasoning or just collecting those facts. So in this case, we generate a sentence according to a recent study, almost 60% of gun deaths are suicides. And finally, we do similar things. We're going to do a premise again, because we want to basically connect everything we have said, in terms of the central claim and also the evidence we just put forward. And here we say, yeah, so by keeping guns out of the hands of those with severe mental health issues, we can greatly reduce gun violence. So this is just trying to show how the system works. But the next big question is like, where we can learn those? What kind of data set we're going to use? So we start a project by thinking about using the Reddit subcommunity Change My View. So I'm not sure whether the audience is familiar with that. It's a community where focusing on facilitating open discussions on controversial issues. Basically, it's structured like discussion threads where a original post will start with a viewpoint on some topic and followed with this detailed discussion and reasons. And other people can reply with counter argument and trying to persuade OP to change their view. And if they do, they actually would award a delta, to show, oh, this argument is really good, it's persuasive. So we want to leverage this type like argument, counter argument structure where the OP will become the input statement and the high quality replies will become the target argument. And I know that you will have the concern like, oh, there are a lot of bad language online, right? So yes, so we use some toxic language detection tools to get rid of those bad language, but we admit that it's not possible to get rid of all of them. Yeah, so then we compare here. I just want to show some results. We compare with retrieval-based methods, which means that just identified, the most likely counter argument from the news. And then we compare with end-to-end trained model. And here's our model's results. We can see that we achieve better blue and root scores. So the scores are based on n-gram matching between the reference and the system generation. So if we further actually ask the model to look at basically what actually the key phrase they're going to talk about, then they actually can further improve the performance. So we also ask a human to look at the output, like are those generations fluent? Actually, does the content make sense? Also, does it cover all those key points we actually should cover? And we find that, so if during the evaluation for each example, we're going to show the system output without the language style control. So probably will not generate so many different types of arguments, our full model, and also finally the human generation. So we can see that the style control definitely helps with all aspects, but there's still a gap between the system generation and also the human arguments here. So here, I think we still have 1 minute. So let me just quickly show a demo that we made where you can actually enter. So this is actually right on top of my, so well, you can enter a argument, right? So here, like the wage gap isn't about gender. There are many government jobs that are seriously dominated by women and happen to pay really low, right? So our system will identify the key phrases, like they're relevant to this generating the counter argument. And then for each of the sentences we're gonna produce, we'll show that what kind of key phrase are using. Like here, this sentence uses wage gap and gender pay gap. And then for next one, chooses something else. It says it's a fact that women are more likely to be able to take care of their children than their male counterparts. So those are the real generations by our system. And then finally, I select something else and then generate like this. Not to say it's unfair to assume that women are being paid less than men, but that does not mean that it's not a case that women are discriminated against. It's not a matter of the wage gap. It is a matter of opinion. So, all right, so I think I'm running out of time. So to conclude, the main takeaway here is that if we're using a model design for neural generation models, we can see that output actually is more relevant, and having a language style control usually is helpful for both fluency and the content. So where we are, so what we're doing at this point with neural generation model is that they can produce fluent sentences. Sometimes they on topic and use the right stance. But what we can also see is that they don't actually good at operating with desired properties we want, like morality, ethics, values, social norms. They in general don't know what are those. And we also want them to be able to perform more complex logical reasoning or moral reasoning, right? And they should be able to update what they believe if they receive new information. And finally, they should consider the target audience, like people may come from different background and then they believe in different things and how we can argue, with that perspective. So thank you very much for listening to my talk. And our work is supported by National Science Foundation. And here are the papers. You can check them from my website, right? I'm happy to take questions if we have time.
Thank you very much. The next speaker in this session is Benjamin Fish. He's also a member of Michigan AI and an assistant professor of computer science and engineering at the University of Michigan. Ben develops methods for incorporating human values into machine learning and other computational systems. He earned his PhD from the University of Illinois at Chicago and did a postdoc at MILA, the Quebec AI Institute, and at Microsoft Research in Montreal before joining us just this fall. His talk is going to be called The Value Gap in Human Algorithm Interaction. Carry on, Ben.
Hello, for those of you I haven't met, I'm Ben Fish. Thank you for the introduction. Today, I'm going to be telling you a little bit about my work on an important part of the interaction between people and algorithms, the algorithm design process. In particular, today I'm going to be talking about reflexive design for overcoming the gap between the values we hold and the formal models like algorithms and much of AI that we design and implement. And I should mention this is joint work with Luke Stark. Formal models form the backbone for a wide variety of computational systems. Formal models include not only mathematical models for use in proofs, but models of the world, the algorithms themselves, and even the code implementing these algorithms. They all help to take a complicated, messy world and discretize, binarize, or categorize it so that it's more amenable to mathematical and computational approaches to learning and decision-making. These formal models are now being used in computational systems to help make decisions about people. For example, a system used to predict the likelihood that a person will pay back a loan in the future then gets used to make a decision about whether someone should or should not receive that loan. In this way, a mathematical model for making predictions is used for deciding questions about should or should not. In other words, the formal model schematizes and mediates our all too human values. Recently, formal models of the values themselves have started appearing in the literature. So for example, differential privacy is a mathematical definition of privacy itself. I won't get into the details of this definition, but such definitions have been proposed for privacy, accountability, fairness, and so forth. So for example, here's another definition, this time for fairness, called equalized odds. For fairness in particular, there's really been a huge number of mutually exclusive definitions proposed. So here's another one called individual fairness. But for these formal models and many more besides, there have been a wide range of criticism. Perhaps values cannot be formalized because they're enacted not through models, but rather human practices. Or even if they can be formalized, it's just too difficult to do so. Or another issue is that this discretization and categorization that I had mentioned is fundamental to formal models, but it ends up being too constraining to the decision-making process and reifying those categories categorized, even when those categories consist of harmful stereotypes. Moreover, creation of these models ends up placing the power to define the values in the hands of designers. Designers you might not trust, or designers you might just disagree with. In response to these issues, the literature and larger communities have taken widely divergent positions on the use of formal models. Very generally speaking, one position has been to not try to worry about values so much in the models themselves. Better to use them as they are and leave it up to policymakers to choose and to create consensus around values. But a second clashing perspective has been that formal models are so problematic that they should be avoided essentially whenever possible, and it's better to simply support meaningful social change instead. Finally, a third response has been full steam ahead with formal models. They're a helpful way to understand values in computational systems. I do believe that formal models can be used, but in this work, what I propose is that formal models can only be used if, in the course of the research and design process, which includes everything from conception to implementation and maintenance, 4 reflexive values should be upheld. These reflexive values are sorts of meta values that focus not only on the actual model itself, but the process of design and the judgments entailed by design. They are values, kind of like privacy or fairness or anything else. But these values are focused on ensuring that all of your other values are upheld in practice. Let's consider what can go wrong when trying to ensure a value holds in a system with an example. In this example, the system evaluates whether an individual should receive a loan to buy a house. And the value in question, we'll just say, is equality of opportunity. In this example, the modelers, the designers, have decided to conceptualize this value as requiring of this system that people and loans similar to those that have been repaid in the past should receive a loan. Now, the system might even work perfectly in the context for which it was designed, but then the system's used in a different context, or the context changes over time. Say to one where if individuals get denied a loan, there's no way to build sufficient credit to ever get a loan, producing a negative feedback loop. Some people never had an opportunity to ever receive a loan, and so the actual outcomes of the system don't uphold the modeler's own value. And this was because of the context the system was being used in. It's also possible to simply conceptualize a value as something wildly different than what it actually is. If a modeler wants to build a system that upholds equality of opportunity, but conceptualizes this value as enabling doing whatever is most profitable, then shall we say there's a large gap between the value and how it's implemented. Thus, the need during modeling for what we've termed value fidelity. Does the conceptualization and implementation of one's own values actually represent those values as they emerge in practice? Heeding this reflexive value means that formal models of values really should only be developed for particular contexts. It also means that there will be technologies that are just so harmful that it doesn't really matter how you design them and shouldn't be used. For our second reflexive value, let's return to the same example. This system had assumed or learned somehow that, just for the sake of example, blue shaded houses got repaid and red shaded houses didn't. But what if reality was just the exact opposite and it was actually blue houses that didn't get repaid? Then people similar to those who repaid don't end up getting the loan from the system. And so even if this conceptualization was a good idea, the inaccuracy of the system's model of the world has normative implications. The equality of opportunity just doesn't happen here. This produces the need for accuracy, which includes not only the accuracy of the outputs of a model, but also the degree to which variables and dynamics used in the model are accurate reflections of reality. Obviously, this is an issue for basically every scientific discipline, so I'm not going to tell you here how to produce accurate models. But it's worth pointing out the old adage that all models are wrong and some are still useful. The goal isn't to produce a perfect representation of reality, but one that's sufficient for actual usage. Accuracy and value fidelity, though, are not enough. For example, what if a system didn't have access to information about previous loans? Then it would be impossible to judge which people or loans are similar to those people who had previously applied. And so even if this ended up being the best way to ensure equality of opportunity, lack of visibility from within the model about relevant information for normative considerations ended up being the problem instead. Or the model didn't have any information about or even acknowledge the existence of feedback loops that I had been talking about earlier. Then there's no way to deal with them. So this produces the need for what we call value legibility. In the case of equality, whatever you want equalized needs to be visible in the formal model itself, or there's basically no hope that it's going to be equalized. Given that it's very difficult to internalize every possible violation of one's values into a model, in practice, this means modelers need to have a plan to account for those effects not formalized in some way within the model. Finally, there's issues that arise from the fact that values are always going to be this contested space. In this example, what counts as similar dictates what equality even means here. The data source of this information about similarity, here symbolized by a color, made assumptions about which features of a person or a loan were important and which were not. This data will usually come from many people, not just the system designers or modelers themselves, people who made decisions about what to include and how to include it. But what if similarity should mean something else? What if everyone's similar or no one is? I can't answer this question for you, but the point I'm trying to make here is that the world around us comes to us with subjective assumptions baked into it. In order to ensure one's own values, modelers need to push back against those subjective assumptions when necessary. We call this value contestation. In shaping the design of a system, formal models concentrate power in the hands of designers. This is a double-edged sword that that requires more than just the participation of a wide range of stakeholders. It requires that modelers not only recognize that values are contestable, they must take part in the contest. These four reflexive values come into play throughout the various stages of the design process. And paying attention to them, I hope, should help modelers in lots of ways. Before a project gets underway, for example, attention to our reflexive values will help modelers decide whether their project is worth proceeding with in the first place. At this stage, which we refer to as a pre-design stage, modelers should pay attention to questions such as whether there are inconsistencies between a modeler's intended normative goals and what they plan to do, and whether the designers themselves can reflect the interests of everyone affected by the system. At this stage, modelers should also focus on refining their normative priors and goals. Having clarity on these can help decide whether it's appropriate to use a formal model in the first place, and if so, which one. Clearly delimited normative priors and goals can serve as hypotheses to test against. In the process of actually designing and developing an algorithm or formal model, Embracing reflexive values will keep modelers focused on how the translation of values into technical language will always be contested and just challenging. These reflexive values foreground the fact that what's left out of the model is as important as what goes in, and that there needs to be some process to account for these choices. Finally, I know the modeling process doesn't actually always happen in a neat order. And so iterative work on evaluating a model's impacts with these reflexive values in mind will help keep a project in line with its original values and goals. And when users are impacted by a model, and they usually are, their responses should be grounds for further series of reflection or evaluation. I'm also well aware of how messy this process is, and I hope this work will inspire modelers of all stripes to try out our methods and iteratively improve on them as well. My focus here is in articulating these reflexive values for formal modeling and pointing out how they can improve the translation of human values into the design process. I hope this can inspire a wider range of work to bring lots of ideas from the social and political sciences into human algorithm interaction and the wider intersection of computational techniques and normative questions. Speaking of questions, I'd be happy to take any either now or in the Birds of the Feather session. Thanks for your attention.
Thank you very much, Ben, and to Lou. Those were two very stimulating talks, and we will have an opportunity to have discussions and questions at the Birds of a Feather session.